So back in grade 9 and grade 10, you did a lot of work on finding the slopes of lines. And so that was trying to put a number to how the thing changed, right? Rise over run. And then in grade 10, you did a whole bunch of work about parabolas. And then in grade 11, you did a whole bunch of work on other functions, like the exponentials and the rationals and the sines and the cosines. And not once did anybody say anything about slope for those curves. And if you take a look at this parabola I've drawn for you here, you maybe can appreciate why. The slope of the parabola here, I don't know what the number is exactly, but it has an upward slope. And here, it has an upward slope, but if I grab a marker there, it's not as steep as it used to be. And in fact, at the vertex, the slope of that thing is 0. And then after the vertex, the slope goes negative. So the reason you didn't talk about slopes for those other functions is that the slope of those functions is different depending on where you are. And up until that point, or up until this point, you haven't had the algebra skills you need in order to actually determine the slope of one of these curves at any particular place. So we're going to do a really clumsy version of it. And if you want a more elegant version, you should take the calculus course, because that's the entire purpose, well, half the purpose, I guess, of calculus, is to determine the slopes of exotic functions. But we're just going to do some numerical examples here to get ourselves warmed up as a pre-calculus event. So the thing I'm going to start with then to try and get this done is to start with the slope of a secant to this line. So let me jot that up there. Slope of a secant. Now, a secant is a line that just cuts through the function. So I might draw one from here to, let's say, here. So there's my secant. 1, 2, 1, 2. Like so. Okay. So if I'm going to do a slope, I need to have the rise, so how much the function goes up or down, and then I have to divide it by how far it takes to do that. So in this particular function, I have a triangle forming, if you can see that there. Got this little piece here, drops that much, and then it runs that far. Now I could just count those because I happen to pick convenient places. But if I were to try and do this algebraically, the slope, change in y over change in x, I'm going to have to figure out how high this is, first off. So to figure out how far up you go on a function, you just need to take the x value and plunk it in for x and do some calculating. So this particular place is when x is 7, and this particular place is when x is 1, 2, 3, 4, 9, 10, 11, 12, 13. 1, 2, 3, yeah, 13. So I'm going to be determining the slope of a secant on f of x between x equals 7 and x equals 13. Okay. So in order to find out this height here, I'm going to have to take the function and I'm going to have to evaluate it at 7. And then I'm going to have to take the function evaluated at 13. And I'm going to have to subtract the two values. So this thing drops, right, is the difference between here and here. Underneath, I'm going to have to take the gap that this thing goes horizontally. So it goes from 7 to 13. Okay, so to do a little work here, the function at 7 would be -1/4 of 7 minus 9 squared plus 11. So 7 minus 9 is -2. -2 squared is 4. And -1/4 of 4 would be -1. -1 plus 11 would be 10. So when I work this out, then the slope f at 7 is 10. Now I still need to evaluate this thing. 7 minus 13 is -4. I'm just going to erase this then. And I need to get the function at 13. So that would be -1/4 13 minus 9 squared plus 11. 13 minus 9 is 4. 4 squared is 16. Quarter of 16 would be 4, so I end up with -4 plus 11, which equals 7. So the value of this function here at 13 is 7 high. Right. So to finish off here then, 10 minus 7 would be 3, or -4. So I end up with a slope for this secant of -0.75. Or you could leave it as this fraction. Slopes are sometimes more useful as fractions. And if we check here, this thing drops 1, 2, 3, and over. Something funny happened there. 1, 2, 3, 1, 2, 3, 4. Hello, friends. 7 minus 13 is 6. So that's -1/2. So if you can actually do algebra correctly, or I suppose in my case it was subtraction correctly, you can see this line is dropping 1 over 2, dropping 1 over 2, dropping 1 over 2. Right? So all we've done there in order to get the slope of a secant between these 2 points is to evaluate the function at the start, evaluate the function at the end, and then subtract the start x from the or the final x from the start x, and you get a slope. Now if you look at this line isn't even close to the slope of the parabola at that point, right? The slope for my parabola should be a little steeper, and this one, it's not even close. Now if I were to draw a secant here between this point and this point, do you see how it's gotten a little better? And if I drew a secant between here and here, that'd be really good too. And if I drew it between here and here, as I draw this second point closer and closer and closer to this value, my secant starts to approximate the slope of my curve at that place. So I need to take this function then, and I'm going to try and get the value of the slope of the parabola when x is 13 by creeping up slowly with the other point. Now if you can think back a few weeks to an operator that allowed you to creep up on a value but not quite hit it, that's what a limit is. So if I were to take this formula then and change it so that it's slope of a tangent. Now that's a line that just grazes the curve and has the same slope as the curve at its particular point. I'm going to do the slope of a tangent on this function. Instead of between two values, I'm going to say at x equals 13. So I need to change this function a little bit. I'm going to move this so I have a little bit more space. First off, I'm going to keep the 13, and I'm going to make this into some other letter. So I'm going to choose a P just for fun. And what I'm going to do is take this value of P and I'm going to try it at 10, and then at 12, and then at 12 and a half, and then at 12.75, and then at 12.9, and then 12.999, and then 12.99999, and I'm going to keep doing that until I can see a pattern in my limit that's going to tell me what the slope of my parabola is at that particular place. So what I'm doing is I'm taking the limit as this dummy variable here gets closer and closer to 13. Now, if you look at the bottom here, you can see why I can't just put 13 here. 13 minus 13 would be 0, and I'd end up with a division by 0, which is forbidden. So I have to creep up on this value and get as close to 13 as I can without actually hitting it. If I do this, so instead of just plunking in some random other place, if I let it slide in close, I've changed from slope of a secant to slope of a tangent. And so I'm going to use different symbols for that. Instead of delta y over delta x, I'm going to use a d. Delta is the Greek letter for d anyway. And my function wasn't named y, my function was named f. So this is the change in f over the change in x. That's the slope of my tangent right there, when x is 13. So an awkward cut there, and 4 years later, I'm going to try and finish this problem. The way I did it originally seemed to cause some confusion because of how the numbers went in and the algebra that was required. So I'm going to try this in just a slightly different way. But I start with the same pieces. I have the slope equation that's been modified to make it slope of a tangent, because this thing allows the second point of the secant to land on top of the first point. This was the function I was working with, and I had already evaluated the function at 13 to give me a value of 7. So I'm going to put that into my slope expression. So df dx is the limit p goes to 13, the function at p minus 7 over p subtract 13. So to do this, I'm going to have to choose a sequence of numbers that creep up on 13. And then once I have them, this piece tells me I have to put those numbers into the function and evaluate them first before I can do anything else. So I'm going to pick my sequence of numbers that creep up on 13. I'm going to go with 13.1, 13.01, and 13.001. So these are progressively descending on 13. So I'm going to put that one into here. F at 13.1 would be -1/4 of 13.1 subtract 9 squared plus 1. Oh, also it's 11. Get my calculator out here. 13.1 subtract 9 gives me 4.1, and I square that and I get 16.81, and I multiply it by negative 1/4, or divide it by negative 4, whichever way you see that. Gives me negative 4.2025, and I add 11 to that, and I get 6.7975. So we're going to do that again for my 13.01. F at 13.01 would be negative 1/4. 13.01 minus 9 squared plus 11. We'll see what that gives me. 13.01 subtract 9 gives me 4.01. Square that gives me 16.0801. Times that by negative 1/4 gives me negative 4.02 plus 11 gives me 6.979975. And one more iteration of this, 13.001, negative 1/4, 13.001 subtract 9 squared plus 11. I'm probably writing on my face now. It's me 13.001 subtract 9, square it, times negative 1/4 plus 11. 0.9979975. So now that I've got that done, I want to look at my outputs, because this is a lot of calculating and I'd like to make sure they're correct before I get too far ahead of myself. The function at 13 should be 7. So I need a sequence of answers, right? Sequence of outputs that are also approaching 7. So that's close. That's closer. That's closer still. So I do have outputs that are approaching the actual value at 7. So now that I have these numbers go here, and this number goes here. So I'm able to actually do the slope calculation. So I have the function at p, subtract 7, divided by the p-value, subtract 13. So in this iteration, I end up with 6.7975 subtract 7 divided by 13.1 subtract 13. So that's just this expression with this number and this number filled in. It's going to give me on top 6.7975 subtract 7 is negative 0.2025 divided by 13.1 minus 13 is 0.1, which gives me a grand total of negative 2.025. One down. On to the next one. I'm going to need my function at p, 6.979975, subtract the value at the point in question, and then this was 13.01, subtract 13, 6.97995, subtract 7 is negative 0.02005 divided by 0.01. This minus this is that, for a grand total of negative 2.005. Now, this was not your answer. This is not the slope of the tangent. This is just my initial guess at the value of a limit. So I'm looking at that and I'm seeing, I don't know, negative 2. Then I look at this one. The second calculation is also not your answer. What it does is it allows you to establish a pattern between these two numbers. So it looks like, to me, the closer I get to 13, This number out front stays the same. I have a -2 and a -2, but I just end up introducing more zeros. So I'm anticipating when I do this third calculation, which will confirm my pattern, that when I'm done, I'm going to get -2, 0, 0, 0, 5, probably. That's what I'm looking for. Well, let's actually do it. Take your evaluation at that place, 99975, subtract the actual value divided by 13.001 minus 13, which is going to give me 6.9979975. Subtract 7 is -0.002000025 over 0.001, which gives me -2.00025. Now that was the pattern I was expecting, right? Every time I add a 0 up here, I end up adding a 0 in here, but the front value never changes. So to actually get this answer, because this isn't the answer either, I have to extrapolate this pattern to as many zeros as I like. I need to actually land on 13. So it looks like if I were to add, I don't know, 10,000 zeros in there, my answer would be -2.0000000000000. And if I'm allowed to add as many zeros in here as I like, I put as many zeros down here as I like, which means that all this stuff here is basically worth nothing. So there's my answer. The trend in these calculations, as I get closer and closer to 13, right? That and that and that are descending on 13. This and this and this get closer and closer to -2. So that is the slope of my tangent at that particular place. Now that you have the slope of that tangent, you can actually write its equation. So like any line, y equals mx plus b. If you're doing the slope of a tangent, the slope in this case is this df by dx thing. So I have a value for that. It's -2. Now I just need an x and a y pair, and I have them sitting right here. Unlike the secant, you don't have 2 points to choose from because the tangent only touches in one spot, so you're forced to use this pair. So my y value is 7, my x value is 13, -2 times 13 is -26, kick that over, that's 33. So the equation of the tangent on f of x at x equals 13 is y equals -2x plus 33. And if you were to graph that on that parabola, it would clip it in exactly one spot. For the second example, we're going to find the equation of a tangent line on g of x on g of x at x equals 3. So this particular function, g of x, is 3 times 2 to the exponent x minus 4 plus 3. That's an exponential. It's been shifted 4 to the right, up 3, and it has a transformation factor of 3, which I incorporated into this lovely blue sketch of the function. So the first thing I'm going to need when I'm going to draw a tangent is where actually is this on the y value. So first thing, I need to get f at 3. So my equation was 2 times 3 minus 4 plus 3. And that's just the equation of my function with the -4 filled in. So f at 3 is 3 times 2 to the negative 1 plus 3. 2 to the negative 1 is 0.5. 3 times 0.5 is 1.5. So the value of my function at 3 is 4.5. Okay. Now that I have that, I'm just going to check. 1, 2, 3. My function is at 1, 2, 3, 4.5. Perfect. That is the spot I'm trying to build my tangent. There's a lot of calculating to do, so I'm going to sort of vanish this for a minute because I need the board space. But to do a tangent, right, slope of a tangent is df by dx, not delta f over delta x. I need to allow a dummy variable to slide towards the x value I'm trying to evaluate at. So here it will be 3. I need to evaluate the function at that dummy value, subtract it from the value of the function at the value I'm at particular, and then I divide it between the separation between the dummy variable and where I actually want my tangent. So this part I have, f at 3 is 4.5, so I can fill that in. Okay. Now to deal with this part, a limit is asking you to pick a series of numbers that creep up on this value. So I need numbers that get sequentially closer to 3. So I'm going to go with the classic choice of p is 3.1, p is 3.01, and p is 3.001. And once I've made those choices, I have to actually evaluate the function at each of those places. So I will need to do f at 3.1 is 3 times 2 to the 3.1 subtract 4 plus 3. Get my calculator out here. 3.1 subtract 4 gives me negative 0.9. 2 to the exponent, negative 0.9, gives me 0.535886. Multiplied by 3, it's 1.607, plus 3 gives me 4.607660. I'm sure that 6 decimal points will be enough for us to get a reasonably accurate answer. Okay, now that's done, I need to evaluate this thing at 3.01. So the function at 3.01 would be 3 times 2 to the 3.01 subtract 4 plus 3. 3.01 subtract 4 is 0.99, negative 0.99. 2 to that exponent gives me 0.503477775. 3 is 1.5104 plus 3 gives me 4.510433. Dot, 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 but 6 decimal places will probably do. And the last one, I need the function at 3.0001. No overzealous there. There you go, which would be 3 times 2 to the 3.001 subtract 4 plus 3. 3.001 subtract 4 is 0.9999. 2 to that exponent gives me 0.500346667 times 3 plus 3 gives me 4.5 0.01040 dot dot dot, but again 6 decimal places will probably do. But before I get too carried away, when x is 3, the function is 4.5. So as my x's approach 3, my answers should be approaching 4.5, and it looks like they are. 4.6 is close to that. This is even closer, and this is even closer than the other two. So I'm ready to actually take this number, put it here, and this number, put it there, to try and calculate my approximations of the slope so that I can build a pattern and deduce what the slope would be based on reading that pattern. So I've got this here. df dx would be the function at the dummy variable, 4.607660, 660. Subtract 4.5 over the dummy variable I chose, subtract the actual place I want my tangent. All right, so 4.607660 subtract 4.5 is going to give me 0.1076660. This minus that is 0.1 for a grand total of 1.07660. Okay, that's not my answer. With one dot, you can't establish a pattern, so I've got to guess. Let's see what happens in the second iteration. So my value at the dummy variable, subtract the value at the actual place, value of the dummy variable, subtract the actual place. It's going to give me 0.010433 over 0.01 for a grand total of 1.0433. Okay. So I'm going to look at this and I'm going to look at this. I see a 1 sticking around, and I see a 0 sticking around, and I see other numbers that are dropping away. So I'm going to expect that my answer over here is going to be 1.0, let's say 1. I don't think this is ever going to dip below 1. I think it's going to stay a 1 and then a 0, and then there'll be some numbers after it that get progressively smaller. That's what I see from this pattern. So I'm going to run this calculation a third time to try and confirm that pattern. So df dx would be 4.501040 divided by 3.001, subtract 3. This minus that would be 0.001040 over 0.001. And I end up with 1.040. So I didn't quite get to 1 here, but I did have all this stuff drop off. So this vanished. So what is this actually doing? Well, it looks to me like the 1 sticks around. It looks to me like this 0 sticks around. And I think the rest of it is going to eventually decay away to nothing based on what's happening here. Because 0.07 dropped to 0.043, which dropped to 0.040. I think eventually this is going to run out. So as I get closer and closer to 3 on x, this is getting closer and closer to 1. So So I'm going to declare that the slope of my tangent. Now that I've got the slope, I just need to use the x and y pair that I already have in order to generate the equation of a tangent. So as with any line, y equals mx plus b, and in this case, the slope is generated by df dx. So I have 1 as my slope. I need an xy pair, which I fortunately have here. 4.5 on the y, 3 on the x. 4.5 is 3 plus b. Subtract 3 from both sides. I end up with 1.5 is b. So the equation of my tangent then will be y equals 1x plus 1.5. Okay. I'm going to clear off all this mess so I can put my sketch back on. There it is. Okay, so this line here has a y-intercept at 1.5. That's there. And it has a slope of 1. So from this place, it goes up 1 over 1, up 1 over 1, up 1 over 1, strikes the curve right there, up 1 over 1, up 1 over 1, 1 over 1, etc., 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 on forever. Isn't that satisfying? You'll notice that the curve, the blue line here, only touches that green line at that spot. You can see very fine if you zoom in that the blue is just a little bit on this side, reaching up to the point, and it remains on that side of the green line. So I have successfully constructed the slope and y-intercept of a line that grazes that curve at exactly that place. So by doing that, if I erased everything except that spot right there, and I asked you how much this blue function was increasing at that particular place, if you zoom in on that, that blue line and that green line are almost identical in this little neighborhood, which is going to allow you to use the slope of this line to approximate the slope of the function in that neighborhood and to be the slope of that curve at that particular point. Now it's sort of irritating to have to do that calculation at every single point of the curve. That would be a lot of work, right? There's a lot of work just to get this one place. Calculus, the next course after this, will allow you to generate a function that gives you the rates of change everywhere, so that you do one little calculation and you know the rate of change everywhere on that function. Basically, you know the slopes of all the tangents that could ever be on that curve. But there's a long walk between here and there. So for now, you're using instantaneous rate of change, which was the df by dx, the delta f over delta x, the limit of some dummy variable approaching wherever you're trying to take find your slope, the function evaluated at the dummy variable, subtract the function evaluated at the particular place you chose, divided by the distance between the dummy variable and the particular place you're after. So we're going to use this and the limit process in order to crank out instantaneous rates of changes at a particular place, and then use them to make tangents.